Welcome everyone to Anishinaabe Arcs. I want to talk about these indigenous structures, some ways of analyzing them and simulating them, ways that the students can creatively engage with that so they come up with shapes that they're interested in and proud of and can have some reflections about. So first of all, why even teach with indigenous knowledge? Why start that way? It depends on your audience. So to the student, we want them to understand that current forms of mass production produce wealth inequality, environmental destruction, contribute to the decline of democracy, whereas indigenous-based STEM can have wonderful attributes. They can actually address wealth inequality. They can make things more sustainable. They give us models for thinking about a democratic process. For teachers, we want to be able to reflect on some of the problems that our education system has created. So the way that you get these racially stratified results from STEM education, and then how to use these indigenous technology hybrids to offer more creative, flexible, better motivated frameworks for those underrepresented students. And fortunately, those two things are mutually supporting. So if you create STEM from indigenous knowledge, it gets students more engaged. When the students ask you, why should I be doing this? You've got a rationale, you've got a reason, right? You can explain to them how this creates STEM that gives you a more just and sustainable future. So the two work in concert with each other. Now, our current STEM problems contributes to environmental damage. You extract ecological value from nature. It contributes to wealth inequality. You extract labor value from workers, and it contributes to the colonization of our social networks, right? So when we go into Facebook, we're essentially offering up our social networks, our communities as a source of funding for these corporations. They've colonized our social networks, so to speak. So whether it's in terms of environment or in terms of labor, or just thinking about how these algorithms can optimize for, clickbait, right, and turn that into a form of political polarization, you've got value being sucked out of us and extracted. So we don't want that. We want a better way of thinking about it. If you apply a systems analysis, you can see that nature and labor and social expression, those are all ways of producing value. Here it gets sucked up by the factory or the farm, whatever means of production is extracting it. And then even if it's not capitalism, if you're using a communist approach and you have these giant factories, right, and giant mass-produced farms, you're still initiating all sorts of destructive, extractive processes. So it's not just a matter of ideology, it's really in the kinds of STEM practices that we carry out. We don't see indigenous STEM as a solution because we're still viewing it through those colonial lenses, through the mindset of thinking about it as this hierarchy where you have these, simplistic, primitive things at the bottom and more sophisticated things at the top. So part of our mission is to try to get away with that and be able to see the real value behind these indigenous knowledge systems. All right, so one useful tool for doing that is through the view of entropy. You might recall that we learned about entropy in physics classes, right? So you've got gas that's high entropy and liquid that's lower entropy, and a crystalline state is very, very low entropy. It's very predictable. It's very organized. So it doesn't take much information to tell you what that crystalline structure is, whereas something that's very, very dynamic and sort of disruptive, like a gas, that takes lots and lots of information to describe what's going on there. So entropy is not only telling you about the state of organization, it's telling you about the information content in a sense. And that's just what happens in these indigenous knowledge systems. So for example, we worked for quite some time with Navajo groups at Dene Community College on the Navajo Nation and interviewed some of these women who raise sheep. And around these corrals, you get these explosions of biodiversity, of plant diversity. And that's because the sheep are eating plants and pooping out seeds, right? So plants have evolved to do just that. And so you've got this incredible diversity of plant types, and those become the diversity of colors. So these Navajo women are taking those plants and producing dyes. And once you dye the wool, you can then create something that's very low entropy. So you move from the high entropy of biodiversity to the low entropy of the weave. You move back and forth between those, and the value circulates. It doesn't get extracted, right? So that modulation in entropy allows that value to circulate in wonderfully unalienated ways. So you think about that as the high entropy moment and the low entropy moment kind of moving through time like a sine wave, right? We can measure that very precisely in terms of the Shannon-Weaver metric for biodiversity, if we like. But here it is just, you know, at an intuitive sense, right? So you have your low entropy moment where you're making the weave, the high entropy moment where it's in the biodiversity in the plants and animals and so on. You're kind of moving back and forth between those. And the same thing happens in lots of other indigenous production systems. So for example, in Bali, you have these wonderful systems of simultaneously drying out all the rice paddies to kill off the pests, and then flooding the rice paddies to kill off a different set of pests. And in between, you've got very, very high levels of bioproduction and high biodiversity, right? In this particular case, it's about controlled burns. So the Anishinaabe groups here in Michigan use these controlled burns, and you would burn off the, you know, sort of weedy plants that are now turning your nice meadow into something that's a little more bushy, right? So that each time you do that burn, the rains come, those nutrients go back into the soil, and you have another explosion of biodiversity. And we actually have a little simulation. If we have time, I'll show that. And those simulations show how those phases are happening at different spans of time. So you've got very quick phases, maybe every 4 years for the meadow. You've got longer phases, so maybe every 10 years for the bushy areas. And then even longer spans, maybe 70 years, right? So longer than a single human time span, where you're taking the forest area and optimizing it for things like caribou. All right, so these indigenous groups are using this modulation of entropy, and in a sense, that's tapping into the fact that nature also uses entropy modulation. So if you think about genotype versus phenotype, you know, at one point, we're very low entropy, kind of a crystalline structure, right? This single strand of double strand of DNA, double helix. And once you become an embryo and you become a baby and you become an adult, the emergence of all this biodiversity happens. All this huge diversity of biomolecules and bioprocesses and so on. And eventually you reproduce, you create another baby, and so you go back into that low entropy phase. And nature uses this because it's also trying to solve the adaptation problem, the information problem, right? So you want to search over the span of possible genetic forms as much as possible, and you let survival of the fittest and so on sort out who's going to be the winners and the losers. And then you enter another low entropy phase in which mutations and just natural recombination is happening, right? So that the next generation now has another set of genetic diversities that nature can act upon. So moving back and forth between those two phases is also a means that nature uses. And it's also a means that we use in computation. So this is a machine learning algorithm, artificial intelligence, called simulated annealing. And it's also using a high entropy phase where I'm trying to find the best route through all these cities. right? I don't want to go back to the same city over and over again. I want to make my smooth traveling salesperson route, traveling merchant route through all these different cities and optimize so I'm not wasting gas or something. So how do you do that optimization? Well, first you throw it out randomly. You find the best route, thinking about it over big distance spans, and then you slowly cool it, right? And as it cools, you're doing that optimization for smaller and smaller time spans, and eventually you come up with the best route possible. So, and that's not just limited to the traveling merchant problem. There's all sorts of problems in which you want to find, the most optimized path, maybe through an abstracted space rather than through a physical space. So we're really looking at the various ways that we can think about translating between these indigenous systems that do things in ways that are beneficial for biodiversity, beneficial for more egalitarian, more democratized societies, and thinking about translating between that and the way that we teach our STEM education classes. Okay, so now let's zoom down into this one particular case that I'm going to be talking about, Anishinaabe Arcs. So a little history of this. We started out with the Potawatomi School using our beadloom simulation, and they talked to some folks at Northern Michigan University at the Native American Studies Center, and they said, this is a pretty cool set of tools. You guys should check it out. They got in touch with us, Marty Reinhardt and April Landala, and said, hey, could you guys do a virtual wigwam? You've got a 2D virtual beadloom. Why not a 3D simulation? And, if you're a software engineer, you can't let a challenge like that go by. So we said, hells yeah. So we're going to create a virtual simulation, but we don't want to impose our math, right? You want that math coming from the indigenous knowledge. So we asked them for their archive of videos and interviews with elders who knew how to traditionally make these materials, and set out on a research endeavor to find out what exactly is the indigenous perspective on this. So really wonderful, again, ecological reciprocity, right? Just like I was showing you with the Native American case of the controlled burns, you're working with nature in ways that help you pump that value without alienating it and extracting it, but by keeping it circulating in reciprocity with the ecosystem. So you're harvesting, trees in such a way that it doesn't harm the forest and so on. But I was really intrigued by these curves, and we ended up modeling them using parabolas because that's what the math teachers had in their curriculum already, and it was close enough fit. But you can see that's not really a true exact parabola. And the more we looked at it, the more we started to realize, oh, that's really a fit to what's called a Bezier curve. And a Bezier curve, you anchor one end of this flexible rod and you anchor the other end, and then you can twist it and you can push it with little anchor points, right? And it'll form whatever curve you want to within those constraints. But I became curious, who was this Bezier guy? Why was he making these equations? Well, it turns out that Bezier worked for a French car company, Renault, in the 1950s. And he was a company employee, and they said, okay, we want you to work on this one particular problem. We know you're really into mathematics, and computers are coming. And so what we want you to do is to take our old method using these flexible wooden rods, these splines. They're not really rods, it's like a thin slat. Using these flexible wooden slats, these splines, we twist and we make these beautiful sinuous curves, right? But we want to know what are the math equations behind that. So Bezier goes about studying this and comes up with a set of equations for it. And he was really tapping into work that had been done at Citroën, the other French car company that was making some similar designs. But what was so interesting to me is that when I asked the Anishinaabe elders, what is it that's going on here? They would say things like, well, the wood taught us. We talked to the tree people, right? We get permission from the trees when we extract these pieces of wood. The wood taught us how to make these curves. Whereas Bezier, when they asked him about it, he said, "Oh, I discovered that. I invented it. I'm a genius." Right? And he even fought over, trying to make sure that he got the patent rights for it. Not to throw any shade on Bezier, it's just that that's what you do if you're an engineer, right? You secure your patent rights. So you can see the difference between the indigenous knowledge system that's about reciprocity with nature and not having a big head and trying to take whatever you can get, but thinking about things in more egalitarian ways, including sharing with our non-human collaborators in nature, versus the Western view that's always needing to extract that value, right? And if you're an engineer, your company is telling you, hey, if you don't patent this, we're going to fire you, because they want the value of that patent. They want to grab that intellectual property rights. All right. So we've got this wonderful, amazing resource of the cradle that you would create to put your baby on, and the basket that you would make, and the canoe that you would make, and the wigwam you live in. All these things are being created with these beautiful arc shapes. We call them Anishinaabe Arcs. And we set up the blocks-based stimulation system so that the students can just jump in there and start playing around with it and experimenting, right? And then once they do that, they can print out the screen, print a picture of the screen, and then reassemble it as a new physical structure once they've kind of creatively embellished this to do what they want. Because you don't want to tell them, you're just supposed to be loyal to your heritage and replicating this, right? You want them to bring their own sensibilities to it and to say, well, I'm thinking about, going to this career, right? And so I want to think, how could I make that into a cool little cup holder for me? I don't know. You want the kids to be able to have some agency and some creativity in this. That's always missing in those kind of top-down STEM education programs. All right, so to summarize, we contextualized Anishinaabe Arcs with this reciprocal ecological relationship. We analyze so we can translate between the indigenous way of thinking about it and the contemporary STEM classroom. We provide these simulation tools, both so they can replicate the heritage algorithm, and so they can creatively explore it, right, and have their own agency involved, and then physically render them, and then finally do some, thinking, some reflection. All right, so let me switch over here to our actual website. I'm going to back up one, just so you can see what it looks like at the beginning here. So we worked with one of the Anishinaabe language teachers.
Anishinaabe Wigwam.
So we could get the pronunciation right and do a little bit of language survival. We start out just introducing, who are the Anishinaabe and some of the contemporary ways that folks have combined those traditions. So folks doing environmental sciences in concert with indigenous heritage. Douglas Cardinal, Anishinaabe architect, who was one of the first architects in North America to ever use computing in architecture, first of any ethnic heritage. And then we dive into this question of why arcs. So why would you make things arc-shaped? And it turns out to have some interesting, physics answers to that, right? If you try to lash things together, they'll be flexible in the sense that you can move them, but they don't bounce back. And so these arc shapes actually store that information in tension. And so you can create these really strong, flexible structures. And we asked our language teacher to translate some of those physics concepts. So here, elasticity. Zhopska. So using some of those concepts, he was able to now develop some terminology that made sense in the local language. We dive into what folks were telling us about going out in the forest and harvesting these epichiimagok for the modulus of rupture, right? You want the species of tree that can hold the most force.
Epichiimagok.
And then the structures themselves. And so what's the geometry that's being involved here? And then, as I was just showing you, we've got the the actual software, and again, this is blocks-based software, and so all we have to do is drag and drop the little blocks. So here's my vertical arcs and my horizontal arcs. Don't really need all of those, so let me just make the ones that are going vertically. And now I can mess around with that. So I can ask, what happens if I add a little bit of rotation around the z-axis each time that I do this. And it turns out it gives me a bendy arc. And so now I've got this really interesting. Let me bring that up a little bit so I can see it better. So now I've got this really interesting set of structures that I can play around with, and I can move this around, right? I can view it from all sorts of different angles. And so once I move that vertically, now I've got the thing I can print out of the paper printer, and I've got the position of the holes where the arcs go. And so moving now back to our slideshow here. So you've got the students creating these beautiful structures on the screen, and then creatively messing around with them and being quite creative with that. And then we decided to take this off to Africa. So I was in Ghana and showing some of the African simulations, African fractals. And I happened to mention to the students, oh, by the way, we've got this interesting piece we've been doing with the indigenous folks in North America, so with Anishinaabe students. And I showed them the houses and the simulations. And they said, well, what about us? We've got houses too. So we were looking over with the students some of these indigenous designs and realized, wow, there's an interesting opportunity here. So we had the students play around with some designs and physical renderings, and I brought it back to the African-American community here in Detroit, to Oleme Dobbles. I'm showing him here some of the simulations that the Ghanaian students had done, and he runs the African Bead Museum in Detroit. So he's got some of these traditional African necklaces that are made with, glass beads and ceramic beads, but he also has seed beads. So these are beads that come from plants. And so I said to Doubles, if we had a greenhouse, we could grow those African plants right here in Detroit. And here is a structure for a greenhouse that the students have created. And a lot of the students in the reflection phase of Anishinaabe Arcs, a lot of the Potawatomi and Ojibwe students had mentioned greenhouses as one of the things that they would like to see come out of this. So we got a grant to, thanks to the National Science Foundation, we were able to pay some of the local folks and brought in some of the university engineering undergrads to work with us. And used this design. And by that time, Dobbles had already been showing us some of the beads that also had that shape, right? So you've got these kind of organic architectures in Africa, but of course, if you're living around those, you're going to end up using that for all sorts of designs. So Dobbles was excited about the connection to his bead shop, and local folks were excited about, getting some extra work. Students got some wonderful STEM education out of this. And so we created real life structure out of this. We used 3D printing a lot to guide folks. So they were having some trouble reading the blueprints and understanding what it was saying. And so having a little model, 3D printed model, was a great way to just communicate that. And so here's one of the local hires was super excited about what we were doing. We sent this out as a Christmas card. That was back in December. And then here we've got our high school students. So we brought in youth interns, and they learned some electronics for some of the, we want a smart greenhouse. Dobbles calls it the African futurist greenhouse. So it actually responds to the temperature, and it's got digital control for irrigation and so on. And then another part of our NSF grant works with local entrepreneurs. And so they had developed some textiles and some other sorts of apparel that they were selling that was based on the biomaterials that were being grown in the greenhouse. Let me just for an end here, let's switch back to our website, and we can look specifically at what some of the students did. So here's a little overview. Students started looking at these structures, developed creatively all these virtual designs, some of which, I don't even know if you could physically make those even as a little model, but they were having a lot of fun just building things on the screen. And then here's some of the designs they did. We asked them what they wanted to do for their career. And so we said, if you are in the design sciences group, you want to be an architect or a furniture maker or something, you'll be doing this in wood. If you want to go into the environmental group, you'll be using these mushroom-based foam bases. And if you're in the engineering group, if you want computing or electronics for a career, we've got electroluminescent wire. And so they actually created their little 3D models out of this light up wire, which was really fun. Here we've got our pre-post contrasts that we did on our survey, showing statistically significant improvement in their interest in STEM careers. But I think the most powerful part about this was their narrative. So in the reflection, we asked them, what are you thinking about this? And where would you take this? And so this student says, I believe my design represents the two worlds I come from, one being of my native heritage and the other of the technology era. With the completion of my structure, I was able to combine two worlds and accumulate an interest in engineering. My community relies on electricity to keep schools running and businesses afloat, and on and off reservation, the world needs electricity. So this project has really taught me that I can provide and give back to my people. And so that was, I practically cried when I saw that. It was just a really beautiful statement. So thank you so much. Please visit our website. I'll show you, I think I've got a couple links here. So generativejustice.org and csdt.org are the two sites. And feel free to contact me if you want to chat about this. Thanks, everyone.